This is the second speaker. The title is Three Flavors in a Triangle.
Okay.
So please start.
Thank you, Peter. Thank you very much. Good morning, good afternoon, and good evening. Now in Beijing, it's evening. So as you know, in this IVALA meeting, one of the most important problem is related to the equation state of dense matter at nuclear density. So there are actually two key points in this research. One is related to the quark confinement or deconfinement. Another one is related to the strangeness. You know, our normal nuclears, normal baryons are stable. Normal baryons are two flavors. That means composed by valence up and down quarks. So if strangeness play an important role, then we have to have consider the dense matter in three flavors. In this talk, I will try to convince you that if we consider in two flavors of quarks, it could be convenience for us to think about the three flavors in a triangle. So I may show why, first I may show that why three flavor is necessary. The quick answer is because the interaction is very strong. So we have to consider three flavors. And then I will tell you that how the method to model the strong condensed matter and the astrophysical manifestations. Finally, summarize. So first about the necessary of strangeness. So you know, in the gauge theory of quantum field theory, we have photons for QED, quantum electrodynamics, and we have also grounds for QCD, quantum chromodynamics. And we are not sure the quantum gravity interaction. So it may be supposed to be graviton for quantum gravity. So all of these gauge bosons are massless. So you know, the quantum field theory is very complex if we try to think directly the order of magnitude properties of the feature. So it could be easier for us to do if we consider in a potential way. So you know, the Yukawa potential is very convenient for us to think about the order of magnitude calculation. So if we have the massless gauge bosons, that means this term vanishes. So we have a Coulomb-like term, Coulomb-like interaction. So for instance, if we try to model the strong color interaction, usually we have introduce a KR term for confinement. So, but anyway, at a small distance, this KR are approximately zero. So also for strong interaction, the potential interaction potential could also be Coulomb-like. So anyway, if we consider these two cases of so-called condensed matter by either electromagnetic interaction or strong interaction. Let me consider the first case of electromagnetic interaction. So we may think simply the very simple list atom, hydrogen atom, composed by proton and neutrons, proton and electrons. So equaling the kinematic energy to the potential energy, we can have the length scale of the hydrogen atoms, hydrogen atom, and also we can also have the interaction energy. This interaction energy could be proportional to the electromagnetic coupling cube to power 2. So in this case, you can also estimate the density of condensed matter dominated by electromagnetic interaction. We call this kind of matter as electric matter, simply. Electric matter, electromagnetic matter, that's fine, equally. So you can estimate the density to be out of 1 to 2 gram per cubic centimeter. Anyway, you can see that the interaction energy or the kinetic energy is proportional to the alpha square. So because this alpha electromagnetic interaction is very small, is 10 to minus 2 or less. So we can see either electron or nucleons could be non-relativistic. But if we consider a condensed matter dominated by strong interaction, things to become different. Because our case, the strong interaction coupling constant could be very large, either could be approximately 2, even higher than 2. So in this case, the quarks could be extremely relativistic. So in this case, the gluons coupled with quarks can split into a number of quark and anti-quark pairs. These pairs we can also call C quarks. So this C quarks could be very important for us to understand many things. For instance, you know, proton and neutron. Let me explain later. So anyway, because the strong interaction is very strong, so we have to have pairs because quarks are extremely relativistic. But nevertheless, there are a kind of so-called constituent quark model to consider strong interaction. And in this constituent quark model, one can also introduce Coulomb-like potential, and we can also follow the interaction. The case similar to the case of to the case of electromagnetic matter. So we can change only the alpha EM to alpha S, and we can estimate the matter density could be out of nuclear density. That's fine. So we know for a baryon, because the baryon is dominated by a strong interaction, so we have 3 flavors of quarks, 3 valence quarks, and also many virtual or C quarks and gluons. So this valence quarks is very is very important. But also you can see in our real case, for our pressure-free strong matter, the density could be out of nuclear density or a few nuclear density, and you can see the the separation between quarks could be out of 0.5 4 meter, and you can estimate the energy scale could be out of 0.5 or 0.4 GeV. This energy scale is much larger than the mass difference, current mass difference of between among strange quark and up and down quarks. So we can see that strange quark should be very play an important role. But anyway, for the heavier flavors quarks, chum, bottom, and even top quarks, because the current mass or bare mass of this heavy quarks is much larger than 1 GeV. So it's our energy scale is lower than the current mass of heavy flavor quarks. So the heavy degree of freedom may not exist in our problem of equation state of supranuclear density. Anyway, we know for our normal nuclear, we have only proton and neutron, long strange. We can only have C quarks or virtual strange quarks. And these virtual or C quarks should also very important for us to understand and understand many things. For instance, if we try to understand the spin of a proton or even the electromagnetic momentum of a proton, we have to have C S quarks. So virtual quark exist in proton or neutron in nuclear. And in our case, if we consider actual physical dense matter, because in this case, the population of electron is much higher than the population of positron. This is very asymmetric. In this case, virtual quark, virtual S quark, strange quark could be materialized to be variance quark. This is very simple. In a conventional way of two flavors, because more electrons, so more up quark is converted to down quark, and less anti-up quark to anti-down quark. So you finally have more down quark than the number of up quark. Because these quarks are combined in proton and neutrons, we finally have more neutrons than that of protons. This we call as neutronization in a two flavor. But as I told you that we have it is very necessary for us to consider in three flavors, up, down, and strange quark. So up quark may convert because more electrons than positrons. Up quark could be converted to strange quark, and the virtual strange quark less up quark to anti S quark. So finally, we have more strange variance quark. So even for a long strange nuclear, proton neutron, because more electron environment, so finally we may have more strange quark than anti-strange quark. So that the virtual strange quark materialized due to this asymmetry. We call this as strangenization or strangenization. I may explain later. C.N. Yang have this sentence. He told us symmetry dictates inaction. And I think this sentence should be very meaningful for us to consider the state of dense matter at around nuclear density. As I told you, it is very convenient for us to consider three flavors. In this case, geometrically, it is convenient to use this triangle. One point in this inside this triangle, the head to the edge measure the number density of the quark. For instance, for this point, the edge to the head to the upper edge means Nu, U quark number density, and this head measures number density of down quark, and this measures strange quark. For in this edge, because the head to this edge is 0, so this is long strange. This is long strange. So this edge means long strange. For our normal atom nuclear atomic nucleus, we have proton and neutrons. We almost equal number of proton and neutrons. So we are the atomic nuclei are in this region, point A. But for neutron stars, because more down quark than up quark, so should be neutron stars are in this endpoint. But this S point is very extremely symmetric, point S. That means the number of up, down, and strange quarks are almost equal. So if you think that the quarks are free, that means the interaction could be negligible, then we can have so-called strange quark matter. But as I told you, that around the nuclear density, a few nuclear density, the energy scale is around 0.5 GeV. That means the interaction between quarks is still very strong, cannot be negligible. What's the matter? Okay, so I go on. Yeah. So as I told you that for our problem with around the nuclear density, the energy scale is much smaller than 1 GeV. You know, perpetual QCD can only be reliable if the energy scale is larger, at least larger than 1 GeV. Could be better than larger than 10 GeV. So our case, the energy scale is only 0.5 GeV or 0.5 GeV. So interaction is very strong. It could be in a similar case for our atomic nucleus. Our atomic nucleus is composed by quarks, but the quarks are not free. It's grouped together in nucleus. So we proposed more than 10 years ago that even in this point S, so the strange quark matter, inside the strange quark matter, the quarks could also be grouped together in a so-called quark cluster, similar to the case of atomic nuclear. So we call this as quark cluster. Now we call this as, we rename the quark cluster as strontium. So how to model the strange quark matter? As I told you that if you think the quarks are free or the interaction could be negligible, as you know, not that in 1984, Edward Witten wrote that the likely Fermi momentum in a quark matter is order of 300 MeV, more than the strange quark mass. So it could be energetically favorable for some of the long strange quark, proton, neutron, up and down quarks to become strange quarks. And finally, we have a strange quark matter in bulk considers true ground state. And many back model with coupling non-zero alpha S prove this conjecture, or so-called Witten's conjecture. But if the interaction is very strong, how to model the quark cluster matter or strontium matter? I think a so-called linked back model could be applicable. This is an older story. Actually, in 1992, Professor Zhang, one of our colleagues in our campus, proposed the so-called back crystalline model. And he cut 6 windows for a back. You know, for the conventional back model, no interaction between the hadrons. But if you cut the 6 windows of the quark, of the back, and link the back by these 6 windows, like this, we can have a back linked model or linked back model. So we may expect that we can, Professor Zhang's model is only for 2-flavor nuclear matter. And we may extend Zhang's model to 3-flavor, from 2-flavor to 3-flavor. And we may expect that if the length scale L is much smaller than the common wavelengths, so 2-flavor matter, that means the nuclear matter could be energetically favorable. But if the length scale is larger or even much larger than the common wavelengths, corresponding to the quark number density, quark baryon number order of 10 to 9, then we may expect the 3-flavored quark, 3-flavored strange matter could be energetically favored. But the key point is to have a detailed model. Luckily, we have this model. We just put this model, our paper on arXiv, and you can see. And we use a linked back model. And in our model, we can only have 4 parameters. C1 related to the renormalization point. MS related to the colonel strange quark mass. B2 and B3 is an expansion to the back constant. You know, for conventional back model, we have constant back model B0, B0. But for our linked back model, this constant could be could depend on the chemical potential of quarks. So we expand, and we have this additional 2 free parameter. Totally, we have 4 free parameter, and these 4 free parameter are calibrated by 2-flavor nuclear matter. We can measure nuclear matter 4 quantities: nuclear saturation density, N0, nuclear bonding energy, E0, nuclear symmetry energy, E symmetry, and compressibility, K. So using this measured 4 quantity, we can calibrate our 4 parameters, and then we can extend from 2-flavor to 3-flavor. And we finally found that our strange matter is energetically favorable, and it means our energy per baryon is much smaller than nuclear matter, 2-flavor, or even strange quark matter. And we can also calculate the maximum mass of our strange stars, and the maximum mass could be around 2.5 GeV. And we can also calculate the tidal deformability of our strange matter at of 1.4 solar mass, and the lambda 1.4 could be between 200 and 500, comparable to the observation of GW 1708-17. So strange matter is belong to the older physics. That means inside the standard model of particle physics. But as I told you that our strange young star model can literally explain many things, as I told you, massive pulsars, tidal differentiability, and many others. I talked this in a few times in the IWALA meeting past years. Besides Renxin star, we can also have other different other astrophysical manifestations, so-called Renxin cosmic ray and Renxin dark matter. We are thinking about this. I may not go to details of this. So finally, summary. The summary is very simple, only 2 sentences. As I told you that strangeness should be very, because the energy scale is only 2.5 GeV, much higher than the energy, than the current mass difference between the 3 flavors of quarks. So we have to consider 3 flavors of quarks if we try to understand the equation state of dense matter at a superlunar density. So it could be convenient to consider this picture in a triangle I told you. And this kind of strong condensed matter, the baryon number could be from 10 to 9 to 10 to 57. 10 to 57 correspond to Renxin compact object. 10 to 9 correspond to the critical baryon number. The scale of the 10 to 9 baryon number is out of Compton wavelengths. That means 1,000 fermi. So strangeness should not be negligible if we try to solve the equation state. This is my first summarized point. The second one is I told you strange condensed matter could manifest in 3 different forms: compact stars, cosmic rays, and even dark matter. I suppose that we can test further. Even we have many considerations for the compact object, but in the future we can also consider other forms of the strong condensed matter physics in the future. That's all. Thank you.